So when we're trying to apply this method to the general matrix, A, B, C, D, E, F, G, H, I, we're going to get some nasty-looking fractions in the process of computing our determinant. But my claim was that the determinant is nevertheless going to be a polynomial, only multiplication and addition or subtraction, and no division in our eventual answer. To see why, let's continue this process by trying to clear out the entries underneath the 1 here. And I can do that by subtracting d times the first row from the second row. So that's row 2 minus d times row 1. And likewise, subtracting g times the first row from the third row. That's going to give me that first 1 by itself in its column with zeros underneath. And I'm still going to have b over a sitting here and c over a sitting there. Now things start to look a little messier, because in that second row I'm going to have e minus bd over a, minus bd over a, followed by f minus cd over a. And in the last row, h minus gd over a, gb over a, and then I minus GC over A. Ugh. Well, after all that work, at least we've seen our second pivot position now. And so to keep going, what I'd really like to do is I'd like to divide that second row by E minus BD over A. This is going to be fun. So 1 over E minus BD over A times row 2. So we're kind of trying to contain the mess a little bit here, because we're still going to have 1 in that first row by itself, and the first row is still going to be the same. It's still just going to be B over A followed by C over A. And then I still have 0, 0 down the first column. And I'm, again, containing the mess so that now I have a 1 in this position. But now the second row, third column is going to be this disastrous compound fraction, f minus cd over a, divided by e minus bd over a. And that is not at all easy on the eyes. So let's just not make it a compound fraction. Let's make it into a simple fraction again by clearing the denominators on top and bottom, multiplying them all by a. So if I multiply the top and the bottom of this thing by a, I'm going to get on the top af minus cd. Just a lot nicer to look at. And when I multiply by that same a in the denominator, I'll get ae minus bd. Alright, well that doesn't look quite as disastrous. But then the entries down here in the bottom row are still kind of messy looking. So actually what I'd like to do is, in addition to that, let's clear out the a's from that third row, just so that they don't look quite as nasty. And if I do that, in the third row I'm going to get ah minus bd, gb, followed by ai minus gc. Could be worse. Now our last step is we want to get rid of that ah minus gb in the last row. That we can accomplish with our final row reduction step, which is row 3 minus the quantity ah minus gb times row 2. And the end of all this yuck is, in the first row, something nice, 1, b over a, c over a. In the second row, 0, 1, af minus cd over ae minus bd. And in the last row, 0, 0, and now I get some nasty looking thing. let me put a little asterisk there so that I can write this on its own line, its own special little line down here, because it's going to be the entry AI minus GC, and then I'm going to subtract the quantity AH minus GB times that entry on the second row, third column, which was AF minus CD over AE minus BD. So that's what belongs right there. Ugh. Well, okay, that's not at all friendly looking, but at least our matrix is triangular now. And those are the entries on its diagonal. So all we need to do now is take the determinant of this diagonal matrix, and conveniently enough, the determinant of this diagonal matrix is 1 times 1 times this orange thing. So this orange thing that we just wrote down here on the bottom is the determinant of the diagonal matrix. Oops. And so our only project now is to retrace our steps to get back to the determinant of the original thing by undoing whatever happened to the determinant along the process of computing these row operations. So let's take them one at a time. Starting with, let's start with this row operation right here. Row 3 minus AH minus GB times row 2. What did that do to the determinant? What am I really doing here? What kind of row operation? Right. I'm really just adding a multiple of one row to another row. That doesn't change the determinant. Which means that this nasty orange thing is also the determinant of this matrix. So let me just kind of, as a shortcut. So the determinant of that matrix was also this nasty orange thing. Okay, but then some fun things happen. Then I end up trying to undo multiplying row A by 3, or sorry, row 3 by A, and multiplying row 2 by 1 over E minus BD over A. But actually, I probably should have done this in the first place. This nasty yellow fraction that we multiplied row 2 by, let's clear its denominators as well by multiplying by A. So really what I was multiplying by here was A divided by AE minus BD. So what do I have to do to compensate for those row operations? Right. When I applied each of these row operations, my determinant got multiplied by that amount that I multiplied the rows by. So, going backwards, I should take this nasty determinant that we had from before, and I should undo. So when I multiplied the third row by A, I should compensate for that by dividing this determinant by A. And likewise, when I multiplied the second row by that fraction, A divided by AE minus BD, I should compensate by dividing by that fraction. So I'll get an A down here, and I'll get that AE minus BD up here. So let's compensate for all of that by multiplying through by AE minus BD in the numerator, and then I've got A squared down in the denominator. So what do I have in total here? Ugh. This is going to be AE minus BD times AI minus GC minus AH minus GB times AF minus CD. And then the denominator, this AE minus BD, got canceled. And then the whole thing has been divided by A squared. And that is now the determinant of the matrix at this stage. Now we just need to follow it back the remaining steps. This step is an addition of rows, this step is an addition of rows, so it doesn't change the determinant. So the very last thing I need to do is undo that step. And how do you undo the step where we divided a row by A? What do we have to do to the determinant? Multiply it by A. So when I multiply that determinant by A, I just end up getting rid of one of the factors of A in the denominator of that factor out in the front, the 1 over A squared. And I'm going to get 1 over A times AE minus BD times AI minus GC minus AH minus GB AF minus CD. Okay, so after all of that exhausting business, let's just take this expression here and bite the bullet and multiply it all out. I'm going to have an A in my denominator from this first factor right there. And then upstairs, AE minus BD times AI minus GC. Foil that, and you get A squared times EI minus AEGC minus AIBD plus BCDG. So that's from foiling out the first product up there. And then I'm supposed to subtract, which means I need some more room again. I'm going to subtract what I get when I foil out the second part, which is A squared FH minus AFGB minus AHCD plus BCDG. The reason I was fretting before is that I didn't notice that we actually have one term that appears twice with opposite signs, so that part cancels. And it happens to be the only term that doesn't have an A as a factor, which means we can cancel that A in the denominator from all of our remaining factors. And here's the big finish. We get a formula for the determinant of this matrix, this 3 by 3 matrix. Namely, A squared EI, we cancel one of the A's and get AEI. AEGC becomes EGC. AIBD becomes BDI. The BCDGs are gone. Then I have minus A squared FH, which just becomes AFH when I cancel the A. AFGB becomes just FGB with a plus, because now we're distributing the subtraction. And AHCD becomes HCD. Ugh, man. So after all of that, here is a formula that you may use to compute the determinant of a 3 by 3 matrix. No one wants to memorize this formula. But mathematicians occasionally will use some properties of this, namely that it contains a product of one entry from each row with entries from a different row in a different column. So when I choose for the first term an A, then the other two things I multiply it by have to come from a different row in a different column than A came from. So AEI, for example, the E comes from the second row, second column, I comes from the third row, third column. And then there are some signs, like some of these terms have minuses on them, some of them have pluses on them. How we determine which goes on which is actually kind of a question for abstract algebra, because it has to do with how we are constructing a permutation of the rows and the columns. Again, it's not worth memorizing, but what you're going to do in your group activity is take this formula and rearrange it in a few different ways to discover sort of what are the patterns that are going on inside of this 3 by 3 determinant, and specifically, how does this 3 by 3 determinant related to 2 by 2 determinants that we can find within this matrix? That's the real question. And over the course of the next hour, you're going to build up the process of minor and cofactor expansion, which is a way of relating a 3 by 3 determinant to a series of smaller 2 by 2 determinants instead.